So we've learned about the first fundamental theorem of calculus, and we know that the FTC is a theorem that relates indefinite and definite integrals. So our second fundamental theorem of calculus, which I'll call the second FTC, this is going to relate definite integrals and derivatives. So when we have a function in this form, remember this is called an accumulation function, because we can plug in different values of x, that's the input of our function, and that changes the amount of the area under the graph of g, or between g and the x-axis, that we are accumulating. Also recall that this x is the true variable of this function. So I notice that x is in my upper limit, my function is f of x, so this other variable t, remember that that is called a dummy variable, and it's really just a stand-in, and we'll explore why that is in just a moment. It could be any letter for this particular function. Someone chose t. So if we look at this first example, I think it'll help us understand why we really have this stand-in or this dummy variable, and why our real variable is x. So when I looked at this first example, f of x, this accumulation function, it is a definite integral. I know that because it has limits. So I'm going to apply the first fundamental theorem of calculus to find f. So we're going to find the antiderivative of 3t squared minus 4t plus 6. So using our rules, the antiderivative of 3t squared is just t cubed, or 3t cubed divided by 3. The antiderivative of negative 4t, I'm going to get negative 2t squared, and then plus 6t. I don't need a plus c, I don't need a constant of integration here, because I'm going to plug in my limits. We said this is a definite integral. So when I substitute my upper limit first, I get x cubed minus 2x squared plus 6x. And I'm going to subtract from that my lower limit substituted in. So 2 cubed is 8, minus 2 times 2 squared is minus 8, plus 6 times 2, which is 12. So we end up getting our function f of x is x cubed minus 2x squared plus 6x minus 12. So notice that f of x is a function of x. X is the variable of the function, and it was in our limit. So that t was really just a stand-in so that we could plug x back in. So the t goes away. All right, we could see one more time with the second example that our real variable here is w, because my function is g of w. I also notice that in my limit, I have the variable w. So in this particular function, x is a dummy variable. That sounds funny. X is a dummy. X is a dummy variable. So again, I can understand this by finding my antiderivative of e to the x plus x cubed. So I'm really just applying the first fundamental theorem here. So we would get e to the x plus 1/4 x to the 4th, or x to the 4th over 4. And again, I don't need a plus c. This is a definite integral. And when I plug in my limits, I get e to the w plus 1/4 w to the 4th. So w to the 4th over 4, however you want to write that, minus, when I plug in my lower limit, e to the negative 1, plus, remember those parentheses are real important because I'm going to subtract the second term, 1/4 times negative 1 to the 4th power. So this ends up being e to the power of w plus w to the 4th over 4 minus, let's see, that's 1 over e plus 1/4. And when I go ahead and distribute that, final answer, I've got e to the w plus w to the 4th over 4 minus 1 over e minus 1/4. So that is our function g of w. So again, when we actually find g of w as a function, our dummy variable disappears. It goes away. So when we're understanding the second fundamental theorem of calculus, it's all about accumulation functions, and it's all about taking the derivative of an accumulation function. So let's consider this first example. If I wanted to take the derivative of this accumulation function, well, the order of operations, I would need to first apply my definite integral and find the function of which I'm taking the derivative of. So this dx, our derivative operator, this is going to come along for the ride. And when I go ahead and find the antiderivative of this, remember I'm working with a definite integral here. So I'm going to get 1/3 t cubed, or I could write that as t cubed over 3 minus 2t squared over 2, so that just becomes minus t squared. And I'm going to evaluate that at my limits. And so what I get is I'm still going to have to take the derivative of this, but when I work with what's on the inside, this is now x cubed over 3, or 1/3 x cubed, minus x squared, because I plug in my upper limit first, minus, when I plug in my lower limit, 2 cubed over 3 is just 8/3. It's a funny looking 8 right there, minus 4. So really, the thing I'm taking the derivative of, if you want to simplify it a little bit more, x cubed over 3 minus x squared, that becomes a plus 4/3 because we have a negative 4/3 in parentheses, minus a negative is plus. So now when I go ahead and take the derivative, what I'm taking the derivative of, all of this is my accumulation function right here. So now when I take this last step of taking the derivative of this, notice that I get x squared minus 2x, and that constant 4/3 is its derivative is 0. So this answer here is the derivative of our accumulation function. Notice that the derivative of our accumulation function is the same as our integrand, except it has x instead of t. So generally speaking, the second fundamental theorem of calculus tells us that if we take the derivative of an accumulation function, so like when I am finding the derivative with respect to x of this accumulation function, where x in our upper limit is a variable and a is any constant, the constant won't matter because just like over here, whatever we plugged in for our constant, when we take its derivative, that becomes 0. What I get is the function that was in my integrand, but it's now a function of x and not a function of t. So sometimes we think about the derivative and the integral sort of undoing each other or canceling each other out, and that's not exactly what's happening, but it's sort of what's happening. When we take the derivative of an integral, we do think of those as being inverses of each other, or rather derivatives and antiderivatives. Since this is a definite integral and we're taking its derivative, it's not exactly the same as the derivative of an antiderivative. But all that to say, this is our second fundamental theorem of calculus. So once we get some practice with it, it's pretty easy because we don't actually have to find the antiderivative, or we don't have to rewrite the accumulation function each time. So if I look at this first example, if I'm taking the derivative of this accumulation function, I'm going to get the function that is my integrand, except I will have my actual x value, my true variable of this function, in place of t. So I just get x times the natural log of x plus the sine of x. And again, there's no plus c here because this is a definite integral. And again, to understand why there's no plus c, when we plug in, like if we did this the long way and we plugged in our constant of -2 and subtracted, we would have some type of constant like we had up here, but when we go back and take the derivative of that constant, it doesn't matter what number that is, the derivative of a constant is always 0. So I don't have to worry about having my constant of integration here, 1, because this is a definite integral, and 2, we're taking the derivative of whatever it is. All right, so then in this next example, Same thing here. If I'm taking the derivative with respect to t of this accumulation function, and it's e to the x sine of x is my integrand, I'm going to get e to the t sine of t. All right, for the last example on this page, we're given this function g of x. It's an accumulation function, and we're asked to evaluate g prime of 5 and the second derivative, g double prime of 5. So first, let's find g prime of x. Well, I see that I am taking the derivative of this function, right? If I want the derivative of g, that's the derivative with respect to x of the accumulation function. So g prime of x is just the square root of the difference x squared minus 3. So if I'm finding g prime of 5, oops, I don't know why my computer's going crazy. If I'm finding g prime of 5, there we go. Sorry about that. That is going to be 25 minus 3, the square root of 25 minus 3. So the square root of 5 squared minus 3, which is just the square root of 22. All right, so now if I want to find my second derivative, well, I'm just taking the derivative of this, right? The second derivative of g is just the derivative of g prime. So using my derivative rules, and again, it might help to think of this as a power to more effectively use the power rule. This is g prime of x, not our second derivative. I know that my 1/2 is going to pop out. I'm going to get all this junk to the negative 1/2 power. The chain rule tells me to multiply by 2x. So if I go ahead and clean that up, the 2 and the 1/2 kind of cancel each other out. They undo each other. We end up with x over the square root of x squared minus 3. So that's our second derivative there. So now, if I'm finding the second derivative at 5, well, I'm just going to plug in a 5. So we end up getting 5 over the square root of 22, which is the same, if you wish to rationalize that, as 5 root 22 over 22. So we do have to be careful with the second fundamental theorem, and we'll look at an example at the top of page 57, but I'm actually going to go out to the side and give you a side example that'll help us make sense of that. If you have room to write this near the top on page 57, let's say that I wanted to take the derivative, oops, maybe, all right, let's say that I want to take the derivative of a function. Let's say that it is from 4 to the power of, let's say this is the sine of x up here, and then my function is e to the t dt. So notice that when we are using the second FTC, we said that if x is our upper limit of integration, and really our lower limit could be any constant, that this just gives us f of x. But that theorem doesn't tell us exactly what happens when instead of x, I have something more complicated, something that's a function of x. So maybe even just like an x squared. So again, let's understand what's happening here by actually evaluating the integral first. So I'm going to keep my d dx operator. That's just the operator telling me to take the derivative. But if I actually evaluate my definite integral, I would get my antiderivative of e to the t, which is just e to the t. Maybe I made that too easy, but let's go with it. And then we would plug in our limits, right? So my lower limit's 4, my upper limit is the sine of x. And so again, my d dx operator is coming along for the ride here. When I plug in my upper limit, I get e to the sine of x, and then minus my lower limit, e to the 4th. Okay, so we've done the integral part of this. So we said this expression is equal oops, and my computer does not want to behave tonight, is equal to this expression. So now when we go to take the derivative of this, just using our derivative rules, well, now I'm taking the derivative of e to the sine of x. And I know the chain rule tells me my derivative of e to some junk is e to the junk, so e to the sine of x, times the derivative of the junk. So I get the cosine of x. And then this minus e to the fourth is a constant, so its derivative is 0. So it turns out that when I use the second FTC here, I have to be really careful that if what is up here, my upper limit, if it's not just x, I'm going to have to use the chain rule when I use the second FTC, because ultimately we are taking the derivative of something. And if the thing that I'm taking the derivative of is a composition, I've got to use the chain rule. So this wasn't just an x, this was a sine of x. So I have to multiply by the derivative of sine of x, which is cosine of x. All right, so back up at the top of page 57, that's really what this all says symbolically. So if my upper limit of my accumulation function isn't just x, but it's g of x, maybe it's x squared, maybe it's sine of x, maybe it's just 2x. If that's not a just plain old x, I'm going to have to use my second fundamental theorem, but I'm going to multiply by g prime of x, so the derivative of that limit. All right, in practice though, it's not that bad. We just can't forget the chain rule. So in this first example, again, I'm taking the derivative of an accumulation function. I notice that my upper limit isn't just x, but it's x squared. So when I go to take my derivative, I'm going to replace my dummy variable with x squared, not with x, but I'm going to replace it with what's up here, because that's what we're doing right here. We're replacing it with this entire function g, not just x. So I'm going to get sine squared of 3x squared. But then, because I'm taking the derivative of something where my input was x squared, not just plain old x, the chain rule tells me I have to multiply by 2x. So this piece is our f composed of g, and then the 2x is our times g prime of x. So if I were to clean that up, I would probably just write that as 2x times sine squared 3x squared. Now in the second example, I have two things to worry about. One is that my limit of integration isn't just t, but it's sine of t. But also, I notice that it's the lower limit and not the upper limit. So when this happens, we've got to reverse the limits, because my second fundamental theorem only works when t or x or whatever our variable is the upper limit. But that's not hard. We can reverse our limits. We could do that by just pulling out a -1. So it's like I have a -1 out here, and then my lower limit's -1. My upper limit is the sine of t. I did not realize that this example was so similar to the one I showed you out to the side. Oh well. All right, so now when I take this derivative, the negative just comes along for the ride. It's a constant multiple. So I should get a -1 times e to the square root of the sine of t, because again, I'm replacing this dummy variable x with my variable expression in this limit, which in this, like, it's a whole function of t. But then the chain rule tells me I have to multiply by the derivative of the sine of t. So I have to multiply this by the cosine of t. So I get like negative cosine of t times e to the square root of the sine of t. All right, so for this example below, we have this accumulation function g of x, and we are given a graph of f. So we want to be really careful here. This is the graph of y equals f of x, not the graph of g. So in part A, we are asked to evaluate g of 8 and g of 0. And just like we do when we evaluate anything, I'm going to take my function g of x and replace my x's with 8 and then, well, with 0. So g of 8 is the definite integral from 5 to 8. Once I replace this, I can call this f of x again. Because remember, t is a demi-variable. So of f of x dx. And so from 5 to 8, I'm looking at the area right here. That is a triangle. 4 times 3 times 1/2. That area is 6. All right, I'm also finding g of 0, which is from 5 to 0 of f of x dx. And if you're like me, I don't like my limits going right to left. I like to read left to right. So I'm going to reverse those limits. All right, so I need my area from 0 to 5. So I like to kind of chunk this up. So I've got a rectangle here that is 2 by 2, so that's an area of 4. I've got a triangle here, 2 times 1 times 1/2, that's an area of 1. And then from 3 all the way over to 5, I have another triangle. 2 times 4 times 1/2 is 4. So when I go from, whoops, I'm going to keep my negative out front, but my area from 0 to 5, because I'm now going left to right and have that negative out front, my area from 0 to 3 is going to be -4 plus -1. So -5. My area from 3 to 5 is going to be this +4. And so I get a negative times -1, which is just +1 there. And remember, if you don't reverse those limits, if you just go from right to left, area above the x-axis is going to be negative, area below is going to be positive. So no matter how we do it, we should get +1 as our answer there. All right, in part B, we're asked to find g prime and g double prime and then evaluate those both at x equals 2. So let's find the functions first. So again, when I'm finding g prime of x, I'm just taking the derivative of this accumulation function. So the derivative with respect to x of that function is just f of x. So g prime of x is equal to f of x. So when I go to find g prime of 2, what I'm looking for on my graph of f is just f of 2. So when my input is 2, f of 2 is my output -2. All right, when I go to find my second derivative, g double prime, well, if the derivative of g prime is f, then its derivative, f prime, is the second derivative of g. So when I evaluate my second derivative of g at 2, what I need to know is f prime of 2. So again, when I look at my graph at 2, I notice that that's a spot where f is not locally linear. So f prime of 2 is non-existent, and that's because f is not locally linear. You could also say that the graph of f has a corner, but f is not locally linear at x equals 2. All right, in part C, we're asked to give all of the intervals where g is concave up. So if I think about it, g is going to be concave up when its first derivative is increasing, and that also means its second derivative is positive. And g would be concave down when its first derivative is decreasing or its second derivative is negative. So since my first derivative of g is f, I probably want to use that fact because I can look at the graph of f and visually see where f is increasing. So I might say that g is concave up. Sometimes I justify my answer first. Where g prime, and we've already established in part B that g prime equals f, but You could say it again, or you could just roll with G prime, but G is concave up where G prime is increasing. And so this is on the interval from 2 to 5. So again, my graph of f is increasing on the interval 2 to 5, and f is G prime. All right, when I'm giving the locations of the relative minimums of G, I remember that G is going to have a relative minimum anywhere G prime changes from negative to positive. So I could say that. So G has a relative minimum when G prime changes from negative to positive. So kind of starting with the justification, you don't have to start with it that way. This occurs at x equals 3. So again, G prime is f. So on my graph of f, x equals 3 is the only location where the graph of f changes from being negative outputs, to positive outputs. All right, finally, in part E, to really answer this, to really justify our answer and answer this like it's a free response question or something, I might make sure that I'm really clear to the reader what I know about finding the absolute maximum of a function. And this kind of comes back to the extreme value theorem. So the absolute maximum of G can occur at endpoints of a closed interval. So endpoints. Now, we weren't given a closed interval here, and I really think this problem would be better if it stated explicitly that G is exists on this domain from 0 to 8. So the absolute maximum value of G can occur at our endpoints x equals 0 or x equals 8, or at critical values of G. So remember, critical values of G, that's going to be where G prime equals 0 or where G prime is undefined. So G prime is f, and f is never undefined on this closed interval from 0 to 8. But f does equal 0 twice, once at x equals 3 and once at x equals 8, but we've x equals 8 we said is also an endpoint of the interval. So G prime equals 0 when x equals 3. All right, so when we are justifying an absolute max, we would usually want to make a table, a t-table here. And we're going to use our endpoints 0 and 8 and our critical value of 3. And in part A, we already evaluated G of 0 and G of 8. So G of 0 we found is 1, G of 8 we found is 6. So the only thing left to evaluate is G of 3, which again is the definite integral from 5 to 3 of f of x. Or I could reverse my limits and say from 3 to 5 with a negative out front. And so from 3 to 5, my area would be positive 4. The negative out front will make that area negative 4. So when I read the question, it doesn't actually ask me what the absolute maximum is. It turns out that it is 6. It just asks me where it occurs. So we could say that the absolute maximum value occurs at x equals 8. And all of that put together, including our table, is proper justification.